If we compare the size of atomic radius for 4 elements which more or less fit the corners of the entire periodic table, there's a clear pattern in the relative size of these atoms. For instance, increased shielding with added electron rings as we descend down a group or column is responsible for atomic radius getting bigger and bigger as we descend down the periodic table. Thus, atomic radius would be greater for orange than for green, as well as greater for pink than for blue. Going across the table, effective nuclear charge, ENC, makes atomic radius decrease left to right, so it makes sense that atomic radius would increase right to left. To clarify, where ENC is high, atomic radius is low. Where ENC is low, atomic radius is high. This also means that green atomic radius is going to be greater than blue because blue has higher effective nuclear charge. Also, orange is going to be greater in atomic radius than pink because pink has greater ENC. The bottom left will be the biggest and the top right element will be the smallest. But what about the top left and the bottom right? Which one's bigger, which one's smaller in terms of atomic radius? Well, it just so happens that shielding is far more powerful in its influence on atomic radius as compared to ENC. Therefore, in comparing green and pink, green is going to be smaller than pink because pink has a lot of shielding going on with those 4 added electron shells. And so any effective nuclear charge that it has greater than green is just going to be overshadowed by how much more shielding pink experiences relative to green. Anytime we compare the atomic sizes of 4 elements which broadly fit the corners of the periodic table, this order will be true. And I encourage you to pause the video and write this down. Here I chose 4 different elements which less so fit the corners of the periodic table, but we still get the same order of size differences, where the top right is the smallest, then top left, then bottom right, then bottom left is the biggest. Even when we choose 4 elements pretty darn scrunched together, we still retain the same order. So it's probably not too surprising to hear that this order of atomic sizes is the most common amongst any 4 elements that you choose to compare on the periodic table. But something very interesting happens when you choose this set of 4 elements. The bottom left remains the biggest, the top right remains the smallest. However, we flip the other two. The bottom right becomes now smaller in atomic radius than the top left. Same order with these 4, and with these 4, as well as both sets of these 4. Putting these sets together, you may have noticed something very interesting. In each case, the top and bottom elements for any one of these sets of 4 are only a single period difference, a 1 shell difference. So even though, for instance, orange and pink have a lot of shielding, blue and green also do have quite a bit of shielding as well. So because all 4 experience at least similar levels of shielding, any differences between their radial sizes is hardly going to be attributed to shielding. It's hardly going to be because of shielding. Consequently, ENC takes over. Effective nuclear charge is a factor directly related to the horizontal position of our elements on the periodic table. Consequently, ENC takes over. Effective nuclear charge is a factor directly related to the horizontal position of our element on the periodic table. And because pink is far more to the right, where ENC is high in comparison to green, pink's atomic size is going to be smaller than green, even though pink has an extra shell. In other words, that 1 extra shell pink has over green is simply not enough extra shielding to overcome the high ENC difference. But when we shorten the horizontal separation, we shorten the difference in effective nuclear charge. In comparison to green, pink has slightly more ENC, and slightly more shielding, both of which will cancel each other out. This is what's called the diagonal effect, and it's basically the phenomenon that the top left and the bottom right elements are virtually equal amongst a bunch of different variables, such as atomic radius size. We could bring these a unit closer horizontally, and we still have this diagonal effect, where the pink and green are effectively equal in their atomic radii. But if all 4 element boxes are touching, it's equal spacing all around. 1 up, 1 down, 1 left, 1 right. So in this case, shielding would take over. In other words, we would follow the most common ordering we introduced at the beginning of this video. So in a nutshell, anytime we have our set of 4 elements, at least 2 rows, 2 shells of separation, we will automatically defer to this most common ordering we've established. Top right, top left, bottom left is the biggest. It's only when we get down to a single shell difference, where the top is right above the bottom, that the atomic size order is quite variable, and it then depends on the degree of the element's horizontal separation. For instance, if we're super spread out left and right, ENC overwhelms, and the top left size becomes bigger than the bottom right. And remember, the diagonal effect is when the top left and the bottom right are virtually the same because effective nuclear charge and shielding are equally as influential. So they sort of like cancel each other out. No doubt this video was confusing, so I highly recommend that you check out the video on your screen where I go in depth into the concept of what atomic radius is and the different phenomenon behind it, such as shielding and effective nuclear charge.